Probability rules. Okay, so first, please remember that we have actually already seen one graph type that is helpful when dealing with probability. So in this probability rules video, we're going to review again Venn diagram. We are going to introduce tree diagrams, and we are also going to talk about something called Bayes' rule. So first of all, helpful graphs. The Venn diagrams can help us occasionally to understand or see probability better, and also tree diagrams. I will demonstrate tree diagrams a few times, well, 2 times in this video, and the Venn diagram we have just once. In addition to that, something that I want you to remember, I'm going to say recall, is I want you to remember how we deal with and in probability. Specifically, let's begin with the always works formula for connecting different probabilities for 2 different events. So let's say this: the probability of A and B is equal to the probability of A multiplied with the probability of B given that A has occurred. So we've seen this a few days now in class. The idea with Bayes' rule, which is the first thing I do want to introduce before practicing these examples, the idea with Bayes' rule is built directly from this relationship. You see, if for some reason I wanted to solve instead of solving for probability of A and B, if I wanted to solve for the probability of B given A, I can rearrange that quite simply using basic algebra. I'll divide both sides by probability of A. And here we have Bayes' rule. I mean, of course, you want to follow the pattern here, right? Noticing that whenever we're looking at this, let's use a different highlighter. Whenever we're looking at this, on top we have probability of and, A and B. But for the probability on the bottom, notice it's probability of A, which is the item. Let me change that. Which is the item or the event that's being assumed in what we're finding. So we're saying what's the probability of B given that A has already happened, and that's what we're dividing that intersection or that and statement by in Bayes' rule. Now at the end of the video, let me actually flip ahead and show you. I do have this this rule written out in much more detail. This right here is another write-up of Bayes' rule. It's the same thing. I just took it a few steps further by breaking this up into other ways of finding, for example, what is the probability of B, which is this entire string here. As you're doing your reading with your slides and practicing homework, you may notice that the connection here is actually easily seen on those tree diagrams. I won't spend too much time talking about it, but just so you know, that equivalence is something that you would be seeing in the homework problems as you're practicing if you want to. And then of course there's another comment at the bottom about the complement of A, that it can be composed of multiple events. So back to the initial example. We have Bayes' rule on the side for us to think about, and the first example says, according to the American Pet Products Manufacturers Association 2003 through 2004 National Pet Owners Survey, 39% of USA households own at least one dog, and 34% of USA households own at least one cat. Assume 60% of USA households own a dog or a cat. So information, let's highlight some stuff here. Information that certainly should stand out to us. We have 39% own at least one dog. We have 34% own at least one cat. And we have 60% having a dog or a cat. So moving from this problem here, let's see, we are asked some things about probability. This first problem is a Venn diagram problem, but maybe one of the ways that you could identify that yourself is notice we don't have something happening followed by something else happening. We do not have branching type thoughts here. This would not be an appropriate tree diagram. Instead, we have 2 different events or 2 different things that we're looking at. We have owning a dog, owning a cat. So let's take a look here. and what the Venn diagram would look like. Remember from in class we said, you know what, we will represent one circle or one bubble per event that we're interested in. And here, even if you scan ahead, we have dogs and cats everywhere, right? So we represent the two different events that we're concerned about: owning one dog, owning one cat at least, right? So we have this one, we have this one. Let me make those prettier. Okay. All right, and so we will say, I'll let this one be dog, and we'll have cat right here. Okay. All right, so dog, cat. Now we have some information that we care about here, right? Like, for example, we know that for having at least one dog, we have 39% of the time achieved this category, and we know that for cats we have achieved this event 34% of the time. We are further told that the union, the OR of these two groups, is equal to 60%. So for the OR, 60%. This is a bit different than the one we saw in class, actually, because remember from class, whenever we have all of the information and we aren't trying to kind of back up and resolve for things, we were able to start from the inside and solve for that intersection first. But you see here, something interesting happens if you understand OR, because, well, we know first of all 100% is the entire square, the entire Venn diagram, if you're thinking in terms of percent, right? That was the universe we talked about in class. But you know, for OR, what we're seeing here is that between both of these, dog and cat, everything should add up to be 60%. That's what the OR means. It's the union of those two events. So, you know, if I tried to go on here and simply throw the percents into the bubbles, right? 39% for dog, 34% for cat. If I tried to do that, I would actually have an issue right away, because I'm actually making this next statement saying that the union will be equal to 60%. I'm making that untrue. So this is actually kind of a brain teaser. Because the idea is, if these two bubbles in the Venn diagram must add to be 60%, yet I know the total amount for dog and the total amount for cat, can I figure out this intersection? Maybe you can. Maybe intuitively you already see that there's some sort of subtraction involved. Or maybe you prefer formulas, and you remember from class that we have an always formula here, the probability of A or B. Yes, we're talking about dog and cat, but we can follow this pattern, I believe. A or B. Remember we said that that would be equal to the probability of the first event A added to the second event B, subtract the intersection. So even if you are more of a formula type person, I guess you could say, well, I know that A or B is going to be equal to 60%. Where shall I put that? Kind of out of space here. Okay, so 60% is equal to, that's my A or B. I'm going to actually erase that as I write this. Okay, so A or B, replacing that now with the 60% or the 0.60. And then I'm going to say that's equal to probability of A. Well, we know that. It can be cat or dog, it doesn't matter. I'll use dog. Okay, so that's going to be 39/100ths, replacing probability of A. I guess to be consistent here, I'll erase that. Probability of B is what's supposed to be added there, so that's 34%, or 34/100ths. And then we subtract the intersection. Maybe some of you algebra brains prefer this version. Right? But again, the idea is that we end up having 60% is equal to, what do we have here? I think that's going to be a 73. Subtract something, right? You could use an X, you could put the probability of A and B if you want. But certainly 7,300 subtract something should give me 60. Hopefully here everyone is seeing that that means the intersection must be 13% or 1300ths. So let's revise this picture a bit. Trying to make bigger bubbles there. That didn't work. There we go. Okay. Revising the picture, let's put 13% here in the intersection. And then we said dog would be over here on the left, and cat would be here. So to figure out the remaining part, what we'll do then is we'll say, okay, well, if 39% have at least one dog, and I know that there's already 13% of dog represented here in this intersection, I'll simply subtract 39, subtract 13. And we get 26%. Likewise for the cat, we have 34% of the households owning at least one cat, so we'll take 34% and subtract again that intersection to figure out the rest of the amount that goes into the cat section. So we have 21% or 2100ths. Okay, that's our Venn diagram. So now that we already have this nice little picture here, let's proceed through the questions. I think it will be pretty easy with the picture to look at. Question A, or part A, what is the probability that a randomly selected household owns neither a dog nor a cat? I guess there is one piece that we did not put in this picture yet, right? So we had dog or cat, dog and cat, is that 13%. What we did not include, I guess, was the outside of our little universe here, right? I mentioned at the start that 100% of what can happen in this scenario should be represented in this Venn diagram. So if we take 1 and subtract our entire 60% that we're representing here in red, we have 40% of the households owning neither a cat nor a dog. So here the answer is 40/100ths or 40%. Part B. What is the probability that a randomly selected household owns both a dog or a cat? Okay, this is a bit easier, right? Because here we are saying, let me make sure I wrote that correctly. Oh, yeah, it's supposed to be and. I thought that was kind of weird to say both and then use this word. Okay, please correct that to and. Okay, owns both a cat and a dog and a cat. Okay, well, that's the intersection that we just solved for. That's our 13%. Again, notice how nice it is with this Venn diagram. It really does, for problems that are kind of hard to see, maybe you can't see the intersection or you don't know the leftover part as easily, it's not as intuitive. The Venn diagram certainly does organize what's going on so that we can answer these questions easily. Now for part C, what is the probability that a randomly selected household owns a cat if that household owns a dog? This portion of the example is the reason I went ahead with Bayes' rule in the beginning of the problem. You see here what we're looking at is something called conditional probability. This notion of something happening given that something else has already happened. That is Bayes' rule, right? So let's write this. I'm actually going to come up on the side here with maybe a color that you can see a little easier. Okay, so let's see, what does it say? They have a cat knowing that they already own a dog. Okay, so we're curious about the probability of a cat given that we know this household owns a dog. Okay. Looking up top, remember we put the intersection on the top of our fraction and we divide by the thing that we are assuming, right? So first we'll say probability of cat and dog, and then we will divide that by probability of a household owning a dog. Okay, so this is equal to, our intersection is 13% again, and just having a dog in general is 39%. I like to put things in decimals even though I'm reading them as percents. So we should see that about 1/3 of the time, 33% of the time, if a household has a dog, we're going to expect them to also have a cat. So Venn diagrams, very nice. Next, let's move into tree diagrams. Here in this example, what I want you to notice as I read through it is the notion that we have something that then breaks into something else. So there's different tiers within each category. This is one way that maybe you can identify yourself that a tree would be more appropriate than a Venn diagram. A manufacturing firm orders computer chips from 3 companies. 10% from company A, 20% from company B, and 70% from C. Let's color code that so we can remember it all. 10% coming from A, that's great. 20% coming from B, also great. And 70% from C. Okay, so we have 3 different companies. Okay, and then what happens? Okay, some are defective. Okay, so that's the double tier part. First we have the different groups, and then now we're saying, you know what, from within those groups branch, something's happening, right? 4% of A's are defective. Let's make that match A. Okay, 4% of A's are defective. 2% of B's are also defective. So that was green I think I used. 2% of B's. And 0.5% of C's are defective. Okay, so we have chips coming from different places and different amounts, and sometimes some are more defective than others. So a worker discovers a randomly selected chip is defective. Okay, so we already know defective. Okay. What is the probability it came from company B? So first, let's let's write the question, and then we can construct a tree. Let's write the question with statistical or probability type notation, right? Let's do this. We are saying that we know the chip is defective. We are asking the likelihood of it coming from company B. So the question here is, what is the probability that this chip came from company B, given we already know the chip is defective? That's what we're being asked here. Look at all this information that we have to kind of organize. Sometimes the trees will be intuitive. For example, I don't believe it would be very intuitive for me to try to go from defective to the company, right? I mean, first the chips are coming from those companies, and then I can say, oh, some were good, some were bad. So intuitively for me, I would start here with the companies and then branch into what's defective and what's good. Let me show you. And sometimes you'll see these trees drawn in a horizontal manner. I like vertical trees. That's just my personality. Okay, but let's see. So first we have company A, then we have company B, then we have company C. Now what I want you to notice is, because I've drawn this vertical, I always start off with like different levels. Oops. So for example, I will have my first level of whatever's going on, whether it's a decision or something that we're looking at. I will have that listed straight across. Every time I try to use my hand to do the side to side, it keeps flipping the screen. So notice I've put that straight across. And then what I will do is I draw the tree, is I will create a second tier of whatever could happen, right? Like you'll see, I'm going to start branching, and whatever the decisions are from that first, I will actually keep that then in the next little section over. So this is the way the trees work for me. And if you just turn this thing and worked on it horizontal, it's the same concept. Think of it in phase 1, phase 2 type mentality, okay? So I've written the first thing that could happen. First of all, where do these chips come from? Company A, B, and company C. Okay, let's see. And what happens? Let's see. From company A, we have 2 things that could happen, right? The chips could be good, or they could be defective. Company B. Okay, well, if the chip comes from company B, also it could be good or it could be defective. So good, defective. Company C, same thing. Good, defective. So this is the tree showing what can happen. Let's go back now and add the percents on the branches, right? In fact, I'm going to go a little bit above, because whenever we don't have equal likelihood of coming from every one of the initial things, A, B, and C, I need to show the likelihood of choosing that initial choice anyway. So let's see. And the probability of me going towards company A was 10%, so I'll put that percent right here. The probability of me going towards company B, that is 20%. And company C is 70%. Trees are like my favorite thing, actually. They're so nice because once you start branching things together, it's actually the pathways are literally the same as you saying the probability of this and this, right? That's why it's so cool that when you label those percentages, you're going to be able to use this thing very efficiently. Okay, so let's see. So we know that once we have A stuff, it says 4% of A's are defective. Okay, so A, if we're coming from A, 4%, I'll put that right here, are defective. Okay, so when we're dealing with percents, of course, we know if we're talking about just company A, if 4% from company A are defective, then that means that 96%, right, 1 subtract 400, 96% are good. Nice. Moving over here to company B, how many of theirs are bad? They have 2% bad. Okay, 2% of company B's chips are defective. Okay, and then same thinking. We're going to think about company B in its own little section for a moment here. If 2% are bad, then 98% are good. Okay, so 98% are good. Company C, same thing. Be careful here. This one usually catches me. It's such a small percent of defective. Moving that decimal twice. It's an easy slip. There we go. Okay, which gives us let me see what it gives us. So I don't really mess up on this part. Okay, I've got it. Fear not. Okay. So we have that. 99.5% of the time we have good. Okay, so again, going down each branch is an AND statement, right? And then if you need to collect different journeys, that would be or. This journey, or this journey, or this journey. Right. So for instance, this is not going to be from the problem. This is just me I'm going to give you like a visual demonstration. If I said what's the probability, just in general, that that one of these chips came from company A and it was good, I would say, okay, well, here's the path. That's 10% multiplied by 96%. That's the path that would give me a chip from company A that is also good. That's literally how easy it is. Okay. Now, of course, we have conditional probability here. So actually, I think the tree was pretty fun, but maybe the difficulty here is coming from knowing what Bayes' rule is and remembering how to use that. All right, so let's write that out one more time. Probability, company B, given that we already know the chip is defective. We said the pattern is to put AND on top. So probability that a chip came from company B and it was defective. And then what we would always take is whatever we're assuming and put that on the bottom. So the probability of defective. Okay. So let's see. Company B and defective. Let's check that path out first. B's green. I'm going green. Okay. So company B, that's going to be this way, and defective, that's going to be this way. So we're taking this journey down this tree. So for this right here, we have 20% multiplied by 2%. I believe, let's see what that gives us. Okay, that's going to be 0.4%. Not even 0.5%. Okay. Alright, so that's the likelihood of that occurring at the same time. And then, of course, in general, what's the likelihood that something would have been defective? Well, I have several different journeys here that gave me defective. And they were all kind of dependent on where they came from, right? Like, we care, like, for example, you can't just use 4% off of company A. You care about how often the chip was coming to from company A to start with. You have to link those things. So the different journeys that we need to check out would be this defective journey, and this defective journey. So here we have this path. This is going to be 10% multiplied by 4%. And then we also have, we already have this one, and then this one right here, this journey right here to defective, tube, that looks like 70%. And we multiply by that 1.5%. Let's see what we get for those numbers. Okay. So, filling in now, here at the bottom we have the probability of both. That was this right here, an initial decimal that we wrote. And then for defective, so going down each branch is like an AND statement because you multiply down the branches. But then as you collect different branches, you know, because you're saying this path would qualify, or this path would qualify, or this path would qualify. Whenever you collect different branches, that's actually an OR. So collect different branches is OR, so you are adding. Okay, so in other words, I need to add down here this point 0, 0, 4 plus another point 0, 0, 4 plus a point 0, 0. I hope no math person ever hears me saying these decimals this way. Okay, let's see what we get. Very nice. This ends up being, on the bottom here we have, let me bring this up. One and 15% on the bottom, and then on top we still have the same numerator. So when we divide this, what do we get? I'm going to round this to 2 or 3 decimals initially, and then in percent form 1 decimal. So we have, it's almost actually 35%, but I'm going to write this as 34.8% or 34.8% and 0.8%, excuse me. Very cool. Definitely seeing this visually, I think, was kind of helpful. At least for me, maybe for you all too. Okay. We do have one more tree diagram, but first let's do this. Okay, let's take a look at a two-way table, also known as a contingency table. This is something you've probably seen before in this class. So let's take a look at this and talk more about this notion of independent before we see our second tree diagram. So here we have some information about people going through an airport. And it looks like we are concerned about if the person is going to be searched or not, if there's any connection between that and if they are carrying a laptop or not. So we are asked, given this information, would you say being searched is independent of carrying a laptop? Now, I guess we could go ahead and start writing the representation of things, but I'll tell you, when I see a two-way table, I can't help it. I really want to, I like to go ahead and add those totals on each side. It just makes my day better, I think. So let's do that really quickly. Okay, so actually when we add the totals here, we have 72 laptops total. No laptops, we have 348. For being searched, the total there, the grand total is 175. And for not being searched, 247, or 245, excuse me. Remember from class, when we're looking at associations, a lot of times it does make sense to put these things in percentages and then think about which one's going to be response versus explanatory. Then you can look across the graph and look for some connections. That's something we've done before, or at least it's been mentioned briefly before. Oh, we're at the grand total here. In this case, though, we are looking just for independence. So there's actually another way that we can do that without getting those percents and then scanning our eyeballs across each column to look at the balance there. What we can do is we can say, okay, well, if searching and carrying a laptop are independent, then one way for me to write that or ask that would be to say, okay, well, what's the probability that I'm searched in general, right? And is that the same as the probability of me being searched given I was carrying a laptop? Or the person, I'm saying I. Okay? So if these two items are equal, then that means that laptop has no effect on search, right? So then we would say, hey, these things are independent. But if they are not equal, then we'll say, hey, there seems to be some effect happening. Okay, so in general, the probability of being searched, let's see. Search, yes, okay, so down that one, that's going to be that 175 at the bottom there. That's the grand total on that. And then that's out of the 420. Okay, so probability of being searched in general is 172 divided by 420. Okay, now being searched given you have a laptop. Ooh. Now for given, when you're looking at a two-way table, you focus in just on that category or that column. So let's see if I can give you guys a visual. That's going to be nice. Okay, so that means given laptop. That means I need to focus only on laptops. That's my total focus. Given laptop, I am stuck here. I can't look anywhere else in the picture. Nothing else matters right now. Literally just look at the part inside this little box I just drew. Okay, so within that, there were 30 out of 72 searched. And so next, I guess we need to calculate and see if this is about the same decimal. Let's see. That one more time. I didn't get what I thought I was going to get for the first one. Okay. I'm rounding to 2 decimal places. Well, which means I did 3, but let's just do 2, it's easier. Huh. It's slightly different actually. Let's see something. That's 3 decimals on that one. This one would have been I think I typed something in wrong. Well, these are not exactly equal. I think though, because we are looking at empirical data, empirical meaning this was observed data, there's not been an experiment conducted, we could be a little bit more lenient with saying these are pretty darn close to being equal. Remember in class we were quite strict with theoretical probability when we were looking at those cards and saying, hey, king and queen, you know, without replacement, definitely they are not independent, right? That little bit of a change on that example for us in class made a difference. Here, it really depends on how strict you want to be. I would say yes. We'd probably say yeah. It's pretty close to independent. So here's the real deal, right? So this is this independence test. As we go further into the class, we actually have tests where we could say, is that close enough or too far away, whenever we are looking at this actual statistical or empirical data that's been collected. Because again, because this is an observation, it might not be the same as theoretical. The slight difference might just be by chance, right? So we can check and say, this is what I expected, this is what I got. So I'm going to leave this with a close to independent as a yes. But know that it really depends on how strict we're being. Technically, there is some difference there at a thousandth of a point there. Okay, ovarian cancer affects only 1 of 5,000 women. A new test detects this cancer 99.97% of the time when it is present. Unfortunately, it also gives a false positive 5% of the time. What is the probability that a woman who tests positive actually has ovarian cancer? So notice with this problem, there are several different components, and it's not appropriate for a Venn diagram because these things have a tiered effect, right? The woman either has cancer or not, and then the test will say yes or no correctly. So we have several parts here that are kind of interdependent, right? We're branching from one to the next. So let's draw a tree diagram. That's the most appropriate thing for us to use. And what we'll do here is I'll show the journey going to cancer versus not cancer. So 1 out of 5,000 have cancer. 4,999 out of 5,000 do not have cancer. Now, the way I got this number on the right-hand side, this 4,999, is remember at every place that the tree will branch, it should add up to be 100%, or a 1 if you're looking at fractions or decimals, right? So when I knew that 1 out of 5,000 did, then of course for not cancer, I can just simply say, okay, well then that means the other 4,999 did not have cancer, okay? And then when someone has cancer, we have a pretty good system here. It looks like 99.97% of the time we're detecting it. Let's put that in decimal form. And this right here would be the having cancer and not getting detected. So no on that test that often, and then yes on the test here. All right. Okay, and then for not cancer, let's see, do we know? Unfortunately, it also gives a false positive 5% of the time. So when it's not cancer, we also have yes on the test, and we have no on the test. And we said yes occurs 5% of the time. The person we're going to know 95% of the time. Okay. So, looking at this, we are asked, what is the probability that a woman who tests positive actually does have ovarian cancer? So we are asked, what is the probability? We know she got a positive test, but what's the likelihood of cancer given yes on this test? Okay, so again we see Bayes' theorem here, right? The probability of both, which you can write as an and like I have previously, or you can abbreviate it like this, divided by probability of yes on that test. Right. The probability of both, let's see what that is. Cancer and yes, right? To multiply those. I'm not loving this. Probably should have just left this. If I were using a smart calculator right now, I would have left that in decimal form. But I'm not, so we'll just deal with this. Okay. And then probability of yes on the test in general, we have this route here. We have this route here, so we need to get the route for getting yes whenever the person didn't actually have cancer. So that one's going to be, that's this one. And they got yes, right? We have 4,999 divided by 5,000. Okay, multiply that by 0.05. Okay. Again, my rounding may be worse than what yours is at home if you're working with me, because I'm using not a smart calculator. Okay. This is pretty low, which I think actually, let me round. I'll make that to a 4, because the next thing it's 0.0039996. So I'll round that now. Something like that. Okay, less than 0.5% of the time. If someone gets yes on the test, would they actually have cancer? So notice, it seems, looking at this test, that we've got it calibrated in such a way that we would like it to be more likely to say yes incorrectly than to say no incorrectly. Right? Maybe that makes sense in this context, though, right? Like, I think I would rather a test for cancer be more sensitive, because then they'll